This device is a reactionless drive, in the sense that it doesn't need to push against its environment in order to move through it like a car does while traveling along the road, nor exchange any momentum with its environment like a rocket does by expelling its exhaust as it accelerates. This device moves and accelerates through its environment solely using reaction forces that are internal to the device. The spinning arm creates a centrifugal force whose projection onto the vector parallel to the device's length is a sine function throughout time, with a frequency equal to the radial frequency of the spinning arm. A sine function has no average value when integrated over its period, but if we want to know what effect the sinusoidal force acting on the device will have throughout time, we have to be careful about how we perform the integration of the force acting on the device in order to describe its instantaneous velocity. While the sinusoidal acceleration is positive, the device's velocity will increase. While the sinusoidal acceleration is negative, the device's velocity will decrease. This means the only time the device will have a zero velocity is at the start and end of the period of the sinusoidal force acting on it, and furthermore, as long as the force acting on the device is sinusoidal like this graph, where it proceeds according to this phase sequence, it will never have a negative velocity. This means the acceleration integrates over time to pulses of velocity that have an average value, and that over time the device will displace. Furthermore, we can increase the average velocity to produce an average acceleration by changing the frequency of the sinusoidal force. Centrifugal force is proportional to the radial frequency of the revolving mass squared. So if we have a sinusoid whose frequency and amplitude increases at the end of a multiple of its current period, the resulting pulses of velocity will have an increasing amplitude and be more closely spaced, resulting in an increasing average value. The resulting displacement of the device will follow a wiggling quadratic curve. An object with a position that is described by a quadratic curve indicates that object is being acted upon by a constant acceleration, and possibly drag. There are other schemes you can use to increase the amplitude and frequency of the sinusoidal acceleration. For example, if you're trying to accelerate the device in the positive y direction, the ones that generally work are when you increase the frequency and amplitude of the sinusoidal function between the angles 0 and pi, and keep the amplitude and frequency the same or decrease them between the angles pi and 2 pi. So through simply using centrifugal forces and a precisely timed increase in internal energy and frequency, we can accelerate objects without them needing to interact with their environment in order to displace or accelerate. I want to point out here that while the math is clear and the experiment supports the general conclusion, the experiment is optimized very poorly. In order for the integration to come out to an increasing average value, precisely timing the radial acceleration of the arm is very important, and I pre-programmed the servo essentially based upon a guess of what the timing should be, because without positional or speed feedback from the servo, which is not present in this device, you just cannot calibrate it properly. Second, the need to continually increase the radial velocity to create an acceleration is a huge practical limitation of this device. It means that in order to hold a constant position against an external force like gravity, which the device currently cannot do but in theory could, you would need to have the arm spin at an ever-increasing speed in order for it to stay still. Theoretically, there is a simple way to overcome this problem that I would like to explore in future experiments. Firstly, you could just periodically apply a brake to the spinning arm. If you throw a ball into the sky, it takes a finite amount of time for it to decelerate to zero velocity and fall back down. So if the device were to accelerate into the sky by increasing its internal energy, it would have a finite amount of time to decrease its internal energy and re-accelerate before it would lose all of its momentum. You could get rid of the internal energy by simply applying a brake to the spinning arm and dissipating that energy as heat. In general, this is a pretty terrible idea because we'd have to dissipate a lot of heat, but it would technically work. There's another possible way of dissipating the energy, and that is by dynamically switching the way the electric motor turning the arm is wired so that it temporarily becomes a generator, and you try to reclaim the energy you stored in the radial momentum of the arm as electric energy again. Whether or not you can deaccelerate the arm fast enough using this method isn't clear, but is better than trying to waste all of the energy as heat. Until next time, thank you for watching.